Today we're going to be talking about strategy for testing series. We're going to take all of the tests that we've learned so far, put it all together into one package, and strategize about what to try first, how to know what tests to perform to see if a given series converges. Okay, so the first thing that you want to do with any series is test for divergence. Okay, so if you can see right away that, hey, those terms are not going to zero, then you know immediately the series an equals 1 to infinity, is going to diverge. Okay, so that's your first off-road off this highway. If the limit is equal to 0, then the test is inconclusive. Keep trying. Okay. Second thing to check, is this a p-series or a geometric series? Okay, if you can see right away that the series you're looking at is of a specific form, so with p-series, that's a series that looks like 1 over n to the p, where n goes from 1 to infinity, and for a geometric series, it's the sum from n equals 1 to infinity of r raised to the nth power. And we know that if p is less than or equal to 1, this diverges. And if p is greater than 1, this converges. And similarly over here, if the absolute value of r is strictly less than 1, then this converges. And if the absolute value of r is greater than or equal to 1, then this diverges. Okay? So if you see right away, hey, this has one of these two familiar forms, this is a simple way to decide if the series converges or diverges. Okay, so p-series and geometric series we can work with, but what if the series resembles one of those two familiar forms, so p-series or geometric series, but is not one of them. Okay? So given that you have this resemblance between your series and a series that you know how to work with, you should try a comparison test. Okay? So either the standard comparison test or the limit comparison. Okay? So you take the p-series or geometric series that you think is similar, as your standard for comparison. Okay. One thing to be careful about when you're applying the comparison test or the limit comparison test, you have to remember that these only work for series with positive terms. So one way that you could fix that is you could just consider the absolute value of your series, the series of absolute values of ANs, and if this converges, then so does your series. Okay. And by considering the series of absolute values, you can use the comparison test and the limit comparison test without worrying. Okay. Next up, let's say you don't have a comparison that you can see right away, but you notice that the series has alternating terms, or the terms of the series are alternating in sign. So, okay, it's an alternating series. In other words, you're looking at the sum of AN where you can split up each AN as -1 to the n Bn, with Bn positive or non-negative. Then, assuming of course that this is a decreasing series, then you can apply the alternating series test. Okay, and just the alternating series test, you check that it's decreasing and that the limit is 0, and then you're home free. Next up, we can take advantage of the other tests we learned. So in particular, if you see factorials, products, or powers, that's a good indication that you should try the ratio test. Okay, the ratio test is particularly good for factorials, products, and powers. Okay, if a sub n is equal to the nth power of b sub n for some series that you can, for a b sub n that you can deal with reasonably, then use the root test. And then as really your last resort, because there's very few examples where this works better than the other techniques we've discussed, then you can try the integral test. So if a sub n equals f of n for a positive, continuous, decreasing function f of x, then you can apply the integral test. Okay, which says that the integral from 1 to infinity of f of x dx converges if and only if the series from n equals 1 from n from 1 to infinity of f of n converges. Okay, so that's the rundown of our strategies. We've had a lot of practice with them over the chapter, so let's take some examples and see how the strategies work together. Okay. So, first example we'll look at is n minus 1 divided by n cubed plus 1 taking the sum from n equals 1 to infinity. Okay? So looking at this, I see right away the terms are going to 0, so the test for divergence doesn't apply. It's not a p-series or a geometric series, but it looks a little bit like a p-series because it's a ratio of polynomials. Okay, so we notice that it looks like p-series. To see which p-series it looks like, you just focus on the largest terms. So n over n cubed, which is 1 over n squared. Okay? So this is a convergent p-series. So p equals 2 is convergent. So our hunch is we can do some kind of comparison test for this with the p-series 1 over n squared to find that it's convergent. So let's take the limit as n goes to infinity of n minus 1 over n cubed plus 1 and divide that by 1 over n squared. Okay, this is the limit comparison test. Okay, and you do have to verify that the terms here are non-negative. Okay. So then carrying out this limit, we have limit as n goes to infinity of n squared times n minus 1 divided by n cubed plus 1. Okay. We can divide top and bottom by n cubed to simplify matters. And we're left with 1 minus 1 over n divided by 1 plus 1 over n cubed. And this limit is plainly 1 over 1, or just 1. And whenever the limit that you get when you do the limit comparison test is a finite number not equal to 0, so these two series have the same convergence behavior. So the sum of n minus 1 over n cubed plus 1 converges like 1 over n squared. Okay, great. That was our first example. Let's look at the next one. Okay, so we're looking at the sum from n equals 1 to infinity of minus 1 to the n minus 1 divided by square root of n minus 1. And looking at this, test for divergence is out because the terms are going to 0. You have this denominator is getting infinitely large. It's not a p-series or geometric series. It looks like 1 over the square root of n, right? We just have to ignore that minus 1. And that's a divergent p-series. Okay? So this doesn't have much hope of converging if we're comparing it to that, but we also notice that this is an alternating series. So we can apply the alternating series test. Okay? So the AST says check that 1 over square root of n minus 1 is decreasing, which we can confirm by seeing that the denominator is increasing. Okay, yes, because the denominator is increasing. Okay, that's part A of the test. Part B is the limit as n goes to infinity of b sub n equal to 0. And indeed, 1 over root n minus 1, you see this gets arbitrarily large. So this is in fact 0. So it passes the alternating series test, which means that it converges. If you were asked about absolute convergence, the answer would be a probable no because of this fact. It looks like 1 over square root of n, which we know is divergent. But using the fact that it's an alternating series allows us to get conditional convergence. Okay, next example. Just having a smorgasbord of examples today. Let's take the series of n times sine of 1 over n, where n goes from 1 to infinity. Okay, so looking at the terms of this series, it's not obvious to me right away whether these terms go to 0. So let's try the test for divergence. Because I know that n is getting quite large, while sine of 1 over n, it's approaching sine of 0, which is 0, so it's getting quite small. But let's try the test for divergence. So take the limit as n goes to infinity of n sine 1 over n. I could rephrase this as the limit, because again we have this indeterminate, product of indeterminate type behavior since n gets large but sine 1 over n gets small, so we'll put it as sine 1 over n divided by 1 over n. Multiplying by n is the same thing as dividing by 1 over n. So this is the same as the continuous analog. So if I'm taking the limit as x goes to infinity of sine 1 over x divided by 1 over x, what I would get by L'Hopital is that this is the same as limit as x goes to infinity of cosine 1 over x times minus 1 over x squared divided by minus 1 over x squared. This is equal to the limit as x goes to infinity of cosine 1 over x, okay, because you have cancellation here. And this, because this term is approaching 0, cosine of 0 is 1. So this is not equal to 0. So the test for divergence implies that the series diverges. Okay. Let's do a couple more. If we have sum of e to the 1 over n divided by n squared, where n goes from 1 to infinity. This is a tricky one. This e to the 1 over n, well, this is the largest this gets is where n is 1. And that's e to the 1, which is e. And the smallest it gets is e to the 1 over infinity, or e to the 0, which is 1. Okay, so this is a useful fact to keep in mind. So, looking at this series, because this e to the 1 over n is staying bounded and the denominator is going to infinity, we definitely don't want to use the test for divergence. The terms are getting arbitrarily small. This is not a p-series or a geometric series. Not a p-series, but it looks like (1 over n squared) once I take into account that this inequality, right? This inequality could be rephrased as e to the 1 over n is less than or equal to e. This could be rephrased as 1 over n squared is less than or equal to e to the 1 over n squared is less than or equal to e over n squared. Okay? And the series on the left and the series on the right converge. Okay, so series e over n squared from n equals 1 to infinity is just equal to e times the sum of 1 over n squared. And this is a convergent p-series. So we use the comparison test, which says that if you have the terms of your series smaller than the terms of a convergent series, then your series is also convergent. Okay? E to the 1 over n divided by n squared is less than or equal to e over n squared. So because the sum of e over n squared converges, so does our series e to the 1 over n divided by n squared. Okay, and to be completely correct about this, you would need to just confirm along the way that the series has positive terms. Okay, you only can do comparison test when you know that the series has positive terms. So we just put that in here. Positive. Okay. Let's do another example. This is a tricky one. Okay, n factorial raised to the nth power divided by n to the 4n. Okay, looking at this right off the bat, I'm not sure if it passes the test for divergence or not. I think taking a limit of this might be difficult. So we're going to skip the test for divergence, even though it may very well work. Oh, we should make this a summation. Okay. Again, this is n factorial to the n divided by n to the 4n. So we'll notice that, okay, plainly there's no p-series or geometric series at work here. This is huge numbers that don't relate to that framework. But you'll notice that this is an equals bn to the n, where bn is equal to n factorial divided by n to the 4th. Okay? So given that we have that equation, we're going to try the root test. Okay, this says take the absolute value of the nth root of the absolute value of your terms and take the limit as n goes to infinity. Nth root of absolute value of a sub n. Here, this is limit as n goes to infinity of n factorial over n to the 4th. Okay, so this is a more reasonable limit for me to compute. So what I'll notice is this is the limit as n goes to infinity of, well, factorial is just 3 up to n, and n to the 4th is just 4 factors of n. Okay? So one of these n's cancels here. Okay, so it's really limit as n goes to infinity of n minus 1 factorial divided by n cubed. And what you'll notice is that you could take off these first 3 terms, so n minus 1 times n minus 2 times n minus 3. So that's n minus 4 factorial times n minus 1. I'm going to rewrite this over here. So we'll have n minus 1, n minus 2, n minus 3, and then multiply that by n minus 4 factorial, and divide that by n cubed, which is just n times n times n. So what you see is that what you have here is an expression that's going towards 1 as n gets very large, and this is getting infinitely large as n gets large. So I can split up this limit. This part is going towards 1, and this part is going towards infinity, so the whole thing goes towards infinity. Okay? And by the root test, that means that this diverges. Okay? And actually, this computation confirms that even the test for divergence would have worked here, but it would have been tricky to apply. Taking the nth root makes things a little simpler. Okay, let's look at the sum of two to the k over k factorial, where k equals 1 to infinity. Okay, so 2 to the k is looks like a geometric series, but the k factorial makes me think we should try a ratio test instead. So factorials, try ratio test. You might say, well, there was a factorial up here also. Yes, there was a factorial, but it was also raised to the nth power, so it made sense to take a root first. Okay, so the ratio test says take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. In our case, we're using index of k for some reason. That's fine. Absolute value of 2 to the k plus 1 divided by k plus 1 factorial over 2 to the k divided by k factorial. Okay, keep the first one in the same order, flip the second one, and then multiply. So we get limit as k goes to infinity of 2 to the k plus 1 times k factorial over 2 to the k times k plus 1 factorial. And this is equal to limit as k goes to infinity of 2 divided by k plus 1. And that is plainly 0. Okay. And what we know is that when we perform the ratio test, 0, if the result is less than 1, then the resulting series converges, absolutely. Okay, let's do one last series. What if we take the sum from n equals 1 to infinity of 1 over ln n raised to the ln n? Okay, this is a very tricky one, because in its current form, we're not going to be able to compare it to much of anything. So whenever I see weird expressions involving exponentials, I try to put everything into one exponential. So what I mean is 1 over log n to the log n can also be written as 1 over e to the log of log n. Okay. And then raise that to the log n power. So we have a product of those two exponents. Well, I can switch that order so that instead of e to the log n times log n, I'm looking at e to the log n to the log n. And what that equals is 1 over n to the log n. Okay? Now 1 over n to the something looks a little bit like a p-series. Okay, so this is starting to look like a p-series. Okay? And in particular, if we only look at n greater than e to the e, okay, so if n is greater than e to the e, okay, then log n is greater than 1, okay, which means that 1 over n to the log n is less than, sorry, you know what, let's, instead of taking e to the e, let's take e to the e squared. And then this expression is greater than 2. Then given this inequality, we have 1 over n to the log n is less than 1 over n squared. Okay, and at this point, we can say, you know what, let's take n equals 1 to infinity of 1 over log n to the log n. This is just the same as the sum from n equals 1 to infinity of, sorry, it's the same as the sum from 1 to e to the e squared, or the nearest integer to e to the e squared of 1 over log n to the log n, plus the value from e to the e squared, the sum from n equals e to the e squared to infinity of 1 over log n to the log n. So I can consider this inequality to hold for all terms of the series. This is just a finite sum. Okay, and the part that we're interested in is that infinite tail. And for this infinite tail, this we can do comparison with 1 over n squared, since it's also positive. Okay, note that it's positive. So the series converges. That one required a bit of creativity. But again, it just boils down to comparison to a p-series. Okay, I think that will be it for this video. Thank you so much.